Broadcast is now starting. All attendees are in listen-only mode.
Okay, thank you everybody for joining me this afternoon or early this evening. My name is John Goff, leading meteorologist here at the Weather Service in Burlington. And we're going to talk to you for the next 20 to 25 minutes about some radar imagery, some of the basic concepts of radar, and how to access that on the World Wide Web, and what you actually are going to look at when you choose some of the options that are available on our webpage. So this is very informal. This is a post-recorded version of the presentation I gave on the evening of March 29th. There was some audio problems with that presentation. And those of you that are reviewing this now, I apologize for those technical difficulties. But if you are viewing that now, hopefully this will come through good. And you can always email me in the email at the later date if you have any questions. So without further ado, let's go ahead and get started. And these are the few rules before we begin. All phones will be muted. We'll answer a few selected questions at the end of the presentation. Again, this is post-recorded, so this is we're not going to do the questions on this version. It is being recorded, obviously, and we're going to last about 30 minutes or so. Here's the basic outline that I'll be talking to you about. Talk generally about the WSR-88D Radar Network, which is the National Weather Service Radar Network. We'll talk about general concepts of radar operation, concepts of reflectivity and velocity, two key terms when understanding radar imagery and interpolating data. Then we'll move on to the main part of the presentation, accessing National Weather Service radar data on the web, and we'll talk about what you'll look at and what you're seeing there when you choose those options. We'll finally kind of wrap up with some of the radar limitations. It's not all perfectly without some errors and some things that you have to take into account when you view this imagery. And we'll also talk about some radar artifacts, which are basically false returns by the radar that are not really precipitation. So when we talk about the WSR-88D network, it's approximately 160 S-band Doppler radars active across the nation, continuously 24/7 monitoring. And we talk about S-band, we're talking about in the microwave range from 2 to 4 gigahertz. And when we talk about Doppler, it's just a general term of the change in frequency as a target bounces off a distant target and returns to the radar. We hear the Doppler effect frequently when you hear sounds in everyday life, especially if you hear something like a passing train horn that's coming towards you, and then as it passes you, the pitch lowers because the wavelength is stretched out or compressed depending on whether the train is coming toward or away from you. Very similar concepts to radar imagery. So the change in those frequencies, we can actually detect those signals. The radars were deployed back in the 1990s. It's actually 1980s technology, been around for quite a while. And they can detect precipitation type, the intensity of the precipitation, and the motion of the precipitation. Continuous surveillance with near full coverage of the lower 48. And I have a few maps just to show you here. This is the kind of lower 48 map of the CONUS, showing the generally continuous coverage over everywhere east of the Rockies. There are some gaps in the Intermountain West where the population density is a little more sparse and the network doesn't have quite full coverage. So you'll see some areas there in southern Utah, central Nevada, south central Oregon, for example, that don't have full coverage. And we also have radars out in the Hawaii, Alaska area, and then some of the U.S. territories, such as Guam and American Samoa. And there's also some radars over there in South Korea. You'll notice in Alaska, there's quite a bit of scant coverage as you get north of the south coast of Alaska, as you go to the north slopes. Not much out there. In terms of us, particularly here in the National Weather Service in Burlington, we monitor two radars and operate two radars. There are the KCXX radar in Colchester, Vermont. And let me just highlight these for you over here. That's KCXX right here. And then we also operate the KTYX radar, which is out in Montague, New York. And this is valuable for monitoring lake effect snows. Burlington, Vermont, Buffalo, New York, Binghamton, New York, Weather Service offices all use this TYX radar, as opposed to the CXX radar, which is mainly a radar that our office itself monitors. There are two dedicated computer consoles that help operate those radars. They're fairly simple, kind of just PCs there with an interactive screen. And you can change the settings and how the radar works off those computer panels, computer terminals. And there will be times where you can change those, and I'll talk to you about that here in a minute. So in terms of general radar concepts, one of the important things to look at is and understand is something called volume scans and slices. So when I talk about a volume scan, it's a scan of the atmosphere that the radar does, and it turns one complete circle and scans the whole atmosphere, and it does it by slices. So the radar looks at low slices and then slowly pivots up to higher slices of the atmosphere based off of what we want to look at. And so in essence, it kind of traces a cone out in the atmosphere. And so the number of slices could be just a few slices or a lot of slices. It's determined by discrete volume control patterns. So volume control patterns, which I'll just hyphenate or abbreviate by VCPs, there's several of them that we can choose from based off of what we want to look at. The scans are generally takes 4.5 to 7 minutes, but if you're in really active severe weather, they can be done even more frequently, as frequent as 1.5 minutes. So here's an example on the screen of a volume control pattern, and you can see the green, blue, and red, the low, medium, and high slices, and those little numbers are the elevation angles above the surface. So you can see the lowest angle here is 0.5 degrees or 1/2 of 1 degree. You can't point the radar down into the ground. So you got to start a little bit off the surface, and then you kind of pivot all the way up. And so when you do that over time, it's basically tracing a cone in the atmosphere. So it's a three-dimensional kind of view of how the atmosphere looks. And the elevations generally range from 1/2 degree to about 19.5 degrees above the surface. And then it'll reset and start all over again. Again, those scans are 4.5 to 7 minutes. And these scans right here, and I'll just highlight that really quick again, these scans here, there can be just a few, or we can do quite a few based off of how many slices we want to see. If it's really severe weather, you may want to see a lot more slices down here in the lower levels. But all in all, it still traces out a cone. One of the other things to consider is when you're near the radar, those lower beam slices are fairly near to the ground and sees fairly low in storms. But as the distance increases, and considering that you're at the lowest angle, you're already pointing 1/2 degree off the horizontal, you get further and further above the ground. So for example, this is an idealized type situation, but here the lowest elevation is seeing in this part of the storm. But as you get, let's say 50, 75, 100 miles away from the radar, now you're seeing way up here. So as you can see, this is much closer to the ground than here. So you have to make some assumptions, and this is where storm spotters and things of that nature and weather reports come really in handy through social media, for example, because we can make some assumptions on what's happening here at the ground, but we really don't know. This may be 10,000 feet up way over here. So here's the primary question: what volume control pattern or VCP to use? Do you want to see light rain or light snow? Are you operating in just a high pressure, clear skies type of weather day? Is it a thunderstorm day or a severe thunderstorm day? In active severe weather, the faster scans with more slices are preferred because things are evolving very quickly and thunderstorms can go up and down, and you really want to look at those low level returns on radar because that's what's closest to the ground. Under high pressure with clear skies, the slower scans with fewer slices is generally the rule that we use because the radar is old. We constantly are replacing parts every year in these radars that we get them repurposed or are fixed at our national centers and then get replaced. So they're old radars that are in continuous operation 24/7 and have been so for over 20 years. So you don't want to work the radars too hard. And so here's an example of a slice VCP35 right here. You can see that doesn't have as many slices as the one I showed you before. Looks like we only have 9 slices. So that's a slower scan. Use it in a clear air type of high pressure situation. Okay, let's talk about two of the main concepts we're going to talk about here about data that we look at radar. One of them is called reflectivity. The other one is velocity, and I'll talk about that in a moment. For reflectivity is basically pretty simple. How reflective is the target? The more reflective a target, the precipitation is usually, and I do want to highlight that, usually heavier. So we look for orange and red and purple colors on the radar. Less reflective, precipitation is usually lighter, blues and greens. There are exceptions, so melting light snow, when light snow is falling through the atmosphere near the surface, and let's say it's 34 degrees and things are melting, that's a highly reflective target. The snowflake melts, it gets water around it, it shows up really bright. That's one exception. Also, a thing to consider is line of sight. The radar is a line of sight instrument, so it sends out beams, and it does get blocked by mountains and other things, buildings, especially close to the radar. And so in those blocked areas, sometimes that precipitation will appear less reflective because it's blocked by the mountains. So the example you see here is a big severe weather event we had back, I believe, in 2007. I can't remember, May 2007, I believe. But you'll notice here that, highlighting this is a big line of storms that dropped south through the Champlain Valley and produced a lot of wind damage. Very highly reflective, heavy, dense raindrops falling. Whereas behind some of these storms and some of this post-storm environment, some of these areas are not as reflective, and it's lighter rain. Things are moving and evolving from time to time, and as an experienced radar operator, you learn to know what to hone in on and what's really the storms and what's background scattered information that's not real precipitation, or what's light precipitation. So this is an example here of light snow, or maybe some light snow and light rain. You see there's not a lot of bright orange colors in there because snow is generally light to moderate. It can be heavy at times, but even in a heavy snow, you're not accumulating the precipitation rates that you would in a heavy thunderstorm. A foot of snow may occur over 6 to 12 hours, which may be equivalent to an inch of liquid precipitation. Heck, that can occur in 20 minutes in a thunderstorm. So you're not going to get the heavy, bright returns on those reflectivity returns on snow and rain. So it's always going to be more of this lighter blues and greens for the most part. So the second thing I wanted to talk to you about, we talked about reflectivity, is velocity. And velocity is very simple. How is the precipitation moving in relation to the radar? So when we look at velocity, and this is an image from northwest Minnesota and the Dakotas area, the black hole is the radar. There's always going to be a black hole over the radar, even when we look at it here in the station, because the radar, it can't look straight up. The radar can only tilt up to about 20 degrees, and then it has to go back down. So you can't look straight up, so there's like a black hole. There's like a data void region right around the radar. But generally, when you look at the velocity, you want to ask yourself, is precipitation moving away to or toward the radar or away from the radar? And generally, you can change these colors depending on how you view these things, but generally it's set that green is toward the radar and red is away from the radar. So it's very valuable in assessing strong gusts with thunderstorms, whether they're departing the radar, coming toward the radar, and there's a scale up here. You can see these minus 30 to minus 20s, which would be incoming, okay, and then outgoing would be the reds and away. Of course, when you get higher and higher up in the atmosphere, the winds will be stronger, so you're looking for things closer to the ground as possible. In this case, all your greens are coming in on the northwest side of the radar, and all your reds are going away from the radar. So this implies a northwesterly wind direction. And this gray area on the image right through here is kind of what we call the zero line. We call it something like the zero isodop. And this is where you're getting no returns at all. So basically toward the radar here, and the reds are away from the radar here. So you're implying northwesterly winds in this situation. So that's a basic background concept of how to view velocity in WSR-88D imagery. Okay, so let's move on and talk about National Weather Service radar on the web and how to navigate it on our website. The first thing you want to do, and this is similar to almost every Weather Service radar or Weather Service site across the country. Whether you want to look at some Weather Service site in Nebraska or Florida or California, it's almost all the same. There's going to be a radar icon noted by the red arrow there on the side of the page. In our case, it's weather.gov/BTV or /Vermont will also get you there. And you click on that radar icon there. And then there's going to be a host of options under reflectivity, velocity, and rainfall. When you see that, when you click on that radar, you're going to get this site here, and then you're going to see all these options over here of that reflectivity, velocity, and rainfall. There's also some other stuff down here, some national views and some other FAQ stuff down here. I'm going to concentrate on this red box area right here, which is all of our local imagery. That's the most important thing you'll probably want to look at. So let's first talk about reflectivity. I've highlighted just the top red part of that imagery right there. And you're going to have two options, composite or base reflectivity. The base reflectivity, if you choose that option, shows the returns from the lowest elevation scan only. That's only that 0.5 degree scan closest to the surface. Okay? It shows the returns from the radar closest to ground level, but there's always catch-22s when you're analyzing scientific data. There's a lot of interference since you're close to the ground. So ground-based targets, and I'm going to touch on this later when we talk about ground clutter and radar artifacts, from buildings, hills, mountains, and even some other stuff like birds and dust and things of that nature. You can also be careful because as you get further away from the radar on that half-degree slice, you're going to be blocked by mountains. I'll show you some maps here in a little bit about where we're blocked on that half-degree slice. So it can be valuable in looking at stuff close to the radar or, for example, a really tall thunderstorm distant from the radar. But if you're looking for some sort of light, low-level precipitation over in far eastern Vermont or, for example, in St. Lawrence County, New York, from this radar, you're not going to see nearly as much. The other option on the second bullet there is composite reflectivity. And what composite reflectivity shows is the strongest returns from all of the elevation scans we're taking with the radar, whether that's just a few scans or a lot of scans. So just understand that that could be anywhere in the lowest slices or the higher slices. You don't know. Now, we can know here because we can view all the slices individually. On the web, there's obviously limitations on what we can put available. But just understand that that's what the strongest returns that the radar is seeing in that slice at that location. So it can certainly be a good indicator of stronger thunderstorms and show movement. You see on the movement applications here, you've got these little loop options, and you can put them into motion. But those stronger returns, they could be at 8, 9, 10,000 feet, or they could be at 1,200 feet off the ground. So you have just to kind of keep that in mind, that what you're looking at and what you're trying to look at. This is an example of composite reflectivity. These are some thunderstorms down in the Houston, Texas area recently. And you can see some of the stronger returns here on the radar. A lot of light rain up in here. The radar is down here in the Houston area. I think it's over here somewhere. It's hard to tell. A lot of moderate to locally heavy rain here, and then a pretty heavy thunderstorm right along the coast here. And you'll see some composite reflectivity here. So it can be valuable in certain situations. And this is just a graphical concept of composite reflectivity. Again, if you look at the diagram, here's our radar. We're looking at a storm off to the right. It's taking all these slices. When you're looking at base reflectivity, if you can see the storm and it's not blocked by mountains or anything, you're going to be looking at this scan right here. Okay? That's what it's going to tell you what the radar sees there, that lowest half-degree scan. If you choose composite, it could be here, 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 or here. You don't know. So you just take, again, that's just a graphical representation. Keep that in mind when you're viewing composite reflectivity. Can certainly be beneficial, especially during thunderstorms, but you don't know what altitude that is. When we look at velocity, we're going to move down to this next box here, and on the right I'm going to draw the blocks. I didn't highlight that for you by mistake, but it's under this velocity. And we've got base velocity and storm relative velocity. Two very important things. Now I'm going to talk about those here for just a minute. Base velocity shows the picture of the basic wind field from the lowest elevation scan. Again, 0.5 degrees. It's important in identifying gradient winds. When I speak gradient winds, that's just everyday winds. The winds blow north to south, south to north, southwest to northeast, depending on the day. They could be strong, they could be blustery, they could be light. They see those low-level gradient winds. And so it can be important in showing wind shifts, those greens shifting to reds or reds shifting to greens. And it can also be helpful in very strong straight-line thunderstorm winds when we're not dealing with rotational winds like in a tornado. So when we see a big squall line of thunderstorms come in where it's just a big gust front, the winds are all coming in from one direction, let's say from the west, really good imagery to look at. And that touches base on that velocity imagery and how to understand it on those few slides I showed you a few minutes ago, the greens and the reds. Storm relative velocity is also shown at just a half-degree base angle, which I don't show you there, but it shows the wind relative to the target's motion, and that's an important distinction. So when something is moving, you have a background wind field, but the storm is moving, that background wind field may look different, okay? So I'm just going to draw this on the map here. Let me advance to the next slide, which I'll show you a storm relative velocity, a tornado circulation here. Let me clear my drawings off. When something is moving in this direction, let's say from west to east by my arrow here, the winds may be blowing from the south from the gradient flow, but as this thing moves, it's moving into those. So apparent to that target, let's say there's some target here, the wind, since it's moving in that way, will actually, the relative flow will be from the southeast because it's moving in relation to the wind. So as far as that target goes, if you're flying in the airplane, the wind actually appears to be coming from the southeast. And that's how when you deal, if you ever read about how ships tack into the wind and how ships track courses, how the relative wind affects their course, it has a lot to do with how these storm relative winds, or in that case, ship relative winds, are blowing. So for the storm relative winds, the most important application is in tornado detection because it shows rotation. The base velocity can show rotation as well, but you get the true rotation in respect to the moving target with storm relative velocity. So when we get in a highly dynamic situation weather-wise, and there may be some tornadoes out there, we'll start to use the storm relative velocity. And it can pick out those circulations really good, really good. So basically, right here is a really tight tornado circulation, okay? And so the radar is somewhere down here. It's not shown. Let's just assume it's here. It's probably off the screen. Same general concepts with base velocity radar, but it's just storm relative. So what? The reds are away from the radar, right? And the greens are toward the radar. And where they're really close here, you can imply something spinning there. Okay, and the stronger that circulation, the tighter packed and brighter colors that are packed close together like that indicates the higher probability of the tornado. Luckily here in the North Country, we don't get a lot of tornadoes. They certainly can happen. When you get out on the big daddy thunderstorms out there on the Great Plains, vital data to have because we can pick out these big tornadoes out there on the Great Plains. Certainly can happen here, but just remember that's the difference between storm relative velocity and base velocity. So my suggestion to you is on any given day, use the base velocity. On a tornadic type of day, use the storm relative velocity. All right, let me go ahead and clear that out for you. And again, remember both of these are at half-degree elevation scans only. So we're not doing composite velocity or anything like that because it'd get too confusing. Okay, finally, as we move down on the radar options on the web, we have some rainfall options here. So I'll just kind of highlight those by my yellow box here. We have 1 hour totals and storm total. So the 1 hour total is in the past running hour, and that can be anything within the past hour that's running, and it's always highlighted up here that I'm drawing on the screen here by this red box. This is the 1 hour precipitation, and it's from, in this case, 7:56 to 8:56, and it's a running 1 hour total, as long as things are being measured on the radar. In this case, it doesn't show anything. It's not raining. It's probably a clear sky day. But just if you want to know what it is, it's within the past hour. So there's your timestamps. If you go to the storm total radar, that's when the last time the radar was reset. Once we go into a mode where it's not recording precipitation, the radar will reset, and then once it starts recording precipitation, it starts that time at like time 0 and starts recording precipitation until it gets clear again, or we manually reset it. So again, you're going to want to go up here and look at this red box, because that is going to be more variable. The 1 hour is always within the last hour. The storm total could be 4 hours, 8 hours, 1 day, 2 days, 5 days. It depends on what you're looking at. In this case, we're looking here, it looks like it's just a 1 day total, about a 24-hour total. And this is just the amount, the accumulation that the radar is estimating has fallen. And there's a scale down here that you will see that it estimates. Not all estimates are perfect. Some are good, some are bad, and they can change during the day. When I work a big flash flood event, sometimes I'll go through a few storms where it's right on the money. I'll overlay rain gauges over that, and it's estimating it well. Other times, other parts of our forecast warning area, it stinks, and you've got to use other tools or automated rain gauges to get a better idea of what's happened. So be aware that those estimates may be good and they may be bad due to a myriad of factors, and I'm going to discuss those here in just a minute. So let's talk about those. Some data limitations, considerations when viewing online imagery, or even from a meteorological perspective when I'm working at work and working the radar, what I've got to consider, what I'm looking at, and what to believe and what not to believe. It's always going to be the challenge. 2 very important considerations, the radar beam height and beam blockage. Let's talk about those. Beam height, pretty self-explanatory, right? What's the height of the beam above the ground? Remember, that lowest elevation scan is 1/2 of 1 degree, so you start off pretty low, but as you get further and further away, and when you look at our furthest area of our warning responsibility, I'm 100 miles out. I'm 7,000, 8,000, 9,000 feet above the surface. So in an increasing distance, the radar is viewing higher in the atmosphere, and this beam may overshoot the most intense precipitation. You may not see it. So, you have a better, maybe this right here, I'm only 25 miles from the radar. This may only be 1,000, I'm going to say 1,000 feet, 1K feet over the radar. But let's say when I'm looking way out here, and this is 50 miles out, I'm seeing here down to the surface, that may be 8,000 feet, okay? So just remember that, what you're looking at. So the beam height is considered further away from the radar, higher off the ground. You got to keep that into consideration. And so that's an important consideration of all of these things I talked about, really, right? Base reflectivity, base velocity, storm relative velocity, the composite reflectivity, which shows the maximum returns from all the angles. The lowest height it can see anyway is still that 1/2 degree, so you're still limited by way up here. So just keep that in mind. Another very, very important consideration, beam blockage. So the WSR-88D, it's a line of sight radar, so lower beams reflect off of higher terrain and are partially to fully blocked. I've got 3 examples here. The top is no blockage, little low hills. You got medium-sized hills, part of the beam is blocked, so you're only getting about half the information back to the radar. And then a big old tall mountain where the whole beam is blocked. So there's limited to no data on the lower scans that are terrain blocked. So I'm going to show you a couple examples here, and we deal any kind of radars that are in mountainous terrain like us or Binghamton, New York, for example, or many of the sites out west that are in the Rockies have to take this into consideration. So we talked about that 1/2 degree is what you're looking at on a lot of that. Here's the beam blockage map. Okay, all blocked at 1/2 degree east of the Green Mountains. All blocked to the southwest of the high peaks in the Adirondacks. Look at this. It's all blocked out here from our radar. Now, other radars may be able to see a little bit better, for example, Gray Main. And then a small slice that's blocked by, I believe, like Ellenberg Mountain or Mountain Lion Mountain, somewhere out there in northeastern New York, a little slice out here. So if you live in one of these areas and you're looking at the 1/2 degree elevation scan, you're not going to see hardly anything because it's all blocked. Okay, so an important consideration Maybe use composite, even though you don't know composite reflectivity, because you may not know how high it is, but you at least will see something. We've also even got some beam blockage maps at 1.5 degree elevation. They're smaller. I don't show them here. Here's a beam blockage example out in Oklahoma with some snow falling. Lighter returns, right? Not a lot of oranges and reds. Snow's a lot of green and blues. Generally lighter than a heavy downpour. But you can see two beam blocked areas. One down here in the lower part of the screen, and then something right here that's blocking a wedge. Either this is a mountain or a building or something that's being blocked by the radar. I'm not sure exactly where the radar is. It's probably somewhere right in here, but it's hard to tell. Normally you can see a little black hole. It may be right in there. But again, beam blocked areas that you're not able to see any precipitation. Important considerations. When we look at radar imagery online and I'm trying to ascertain whether a thunderstorm is severe in eastern Vermont, can't use the 1/2 degree, so I have to go up several scans to see a better idea. There's a lot of tools that we use that can better identify what's severe and what's not that I'm not really covering here. I'm really just addressing radar limitations, but I wanted to give you a picture of what some of those limitations are. We also have a lot of things called data artifacts, or what we often call as ground clutter. It's unwanted false returns on radar. It's not precipitation, it's just stuff out there that's interfering with the radar, and it usually shows up more frequently on the 1/2 degree scans because remember, those are the closest to the ground. And they can range anything from terrain, so mountains and hills, ground-based objects, especially if they're close to the radar, radio towers, tall buildings, things of that nature, wind farms with the high wind turbines, and even things as crazy as traffic, motor traffic, and birds. And the meteorologist must be able to distinguish the difference between that and what real precipitation is, and we can use some settings on the radar that are a little technical for this discussion to help minimize some of that. But keep in mind, when you look at radar imagery online on the web, a lot of times around Burlington, if you look at our radar, you'll see a lot of this little blue scattered stuff, and it's even on a high pressure day, and it's not really precipitation, it's ground clutter. And if there's areas of known consistent ground clutter, for example, a wind farm, we can actually mask those areas out and tell the radar don't record data from that area or record precipitation, because otherwise, if a wind farm is showing up as really bright orange and red colors, which I'll show you an example here in a second, if we didn't mask that area out, it would just accumulate biblical amounts of rainfall and tell you, put out a flash flood warning. You got 30 inches of rain there. Well, we know it's not happening. It's a wind farm. So the first one I mentioned was terrain, hills and mountains. This is the base reflectivity option off our CXX radar. So the radar again is right here, okay? And you'll see the higher peaks of the greens and Adirondacks. See some of these higher peaks here and here. And there's some summits of some greens in there, and there's, you can kind of imagine some hills in there. So that's the terrain blocking the lower scans, and you're seeing some of that. These areas up here were actually real precipitation on that day, some light precipitation. Whether that's reaching the ground or not, hard to tell. It's pretty far away from the radar, way up there by Montreal. It's 80, 90 miles away, so you got to think, several thousand feet up in the atmosphere. Our next option is our next form of ground clutter is ground-based objects. Generally low-level interfering objects, buildings, trees, dust, insects in the air, especially on a summer evening. It's often seen very close to the radar on lower elevation scans. So again, think that 1/2 degree, that base velocity, base reflectivity. And it's just kind of a little mishmash of stuff in here. You see all this stuff in here that's just kind of around? Speckly stuff, it's not real, it's ground clutter. It's just speckly stuff that kind of just speckles around on the radar every scan you do. It doesn't really move too much other than just kind of speckly, kind of comes and goes. It's not real. Talked about wind farms. Here is the Altona wind farm, way up here in northeastern New York by Altona. There's some other bigger ones, other lines of them out here by Chateauguay up that way. And there's some other ones actually in here, the Georgia Mountain Wind Farm up here. You can see this bright orange-red color. Looks like the radar's trying to show a thunderstorm up there. Get questions about this on social media every year. It's just a wind farm. And so what we've done is we've masked that target out, and we don't process any information from that site, because if you looped through, it would just show that one return sitting there and not moving. So that's a good thing. You don't want to be recording huge amounts of precipitation or showing really heavy rain or hail there when you know nothing's occurring. The real problem is that when a thunderstorm actually goes over that site, because then there could be real data over the bad data. It becomes problematic, as I'm sure you can imagine. Here's some other examples of wind farms. That's our TYX radar out on the eastern end of Lake Ontario, and you can see all the wind farm clutter right up in here. Maple Ridge Wind Farm, huge wind farm complex. So again, when real thunderstorms go over the bad data, you've got to be able to tease that out as a radar operator to figure out what's real. Important considerations. And you can definitely see some of this on the web. You can also see things as silly as moving traffic. We talked about the velocity, the inbound greens and the outbound red signatures on that low-level velocity scan. Well, look here. This is Route 7 coming south from South Burlington, going down, toward the Shelburne area. And you can see little greens and blues and reds of alternating traffic. And most of this is being picked up, if you live in the Burlington area or are familiar with Shelburne, is when you come over that high ground south of Shelburne on Route 7, you pull out of the intersection where you go to the Charlotte Ferry, and then you come up the big hill, and then you crest the hill, and then you start to come down. That's kind of a high ground right there. You're picking up all of that traffic coming and going. Some, depending on the refractive properties of the air and the day in question, sometimes the signatures appear better than others, but that's what you're actually seeing there, which is really, really kind of curious. And the first time we saw that, we weren't sure what we were looking at, and then we finally were able to deduce what we were actually seeing. Then finally, we have things as interesting as birds and insects, often seen in the summer and fall months where birds are near lakes or ponds, and in the morning or evenings when they disperse out for their nightly feeding or their morning feeding to go out to forage, you'll see these balls kind of form over these lake areas and then just expand. So it'll start as like a small little ring, and then over a period of about 30 minutes, it expands into these big ring signatures. You can also see bats in the southern United States disperse out of the caves at night. I know from the San Antonio radar down in the Bracken Cave area, you can see the bats disperse in the evening and morning when they're coming and going. Again, typically a summer-fall occurrence. In the winter, you don't see that quite as much. Usually along lakes and swamps and wildlife refuges, things of that nature. Okay, so let's wrap up with a summary. As you recall, I talked about our WSR-88D network. Those are S-band 160 radars, about 2 to 4 gigahertz on the microwave spectrum. There's a number of them across the nation, pretty full coverage across the lower 48, a few gaps in the Intermountain West. Also in U.S. territories, a little bit more scant coverage, for example, in Alaska, especially in northern Alaska. We talked about general concepts of radar operation, volume control patterns, the slices the radar takes, how we can control how fast those slices are taken or how many. We also talked about the main concepts of reflectivity, how reflective the rainfall targets or snowfall targets are, and velocity, how those targets are moving in relation to the radar. And we also talked about storm relative velocity, how the wind is blowing in relation to the moving target, more advantageous to look at during tornadic storms. We then moved on to navigating weather service radar on the web and how to access that information, and also talked about important radar data limitations when you're looking at radar data, especially in those lower elevation scans, where a lot of that imagery is either blocked and partially contaminated by low-lying objects. As we touched on that, we moved on to the radar artifacts, mainly things like ground clutter. Talked about blockage of the beams due to high terrain, general ground clutter near the radar site, which could consist of buildings, trees, bugs, insects, what have you, and other things such as traffic patterns, bird dispersions off of lakes, and things of that nature, and even covered some of the problems and problematic issues we deal with wind farms and how we have to block some of that data because we don't want to process bad data at those sites. So that's all I have for you. Thank you so much for listening. And if you want to send me an email, you can, if you view this presentation, since this is being recorded out of the GoToWebinar series, you can email me at john.goff, it's John with an H, .goff, 2 F's as in Frank, @NOAA, NOAA.gov. John.goff @NOAA.gov. I appreciate you taking a few minutes to listen to this presentation about radar imagery, and have a good rest of your day. Thanks a lot.